there are some questions on what we did in the last class. Let us clarify some of the doubts, because I know that there has been a jump in the level of the subject which we have been dealing with till last class, and a lot more mathematics was involved in the last class. So, let us just recapitulate what we did and clarify certain of the doubts. The first confusion that usually students have is what is the difference between stress vector and stress tensor. Okay. The first thing that you should understand is that tensor is a generic name, okay, generic name. Tensor can be 0th order, okay, 0th order. Zeroth order tensor is nothing but a scalar. The first order tensor, is called as the vector. Then the tensor keeps moving to second order, third order, fourth, and so on. Is that clear? So, it is a generic name. Now, the question is, what is a vector and what is a stress vector and what is a stress tensor? If you remember, we were dealing initially for the definition of stress, okay, a vector quantity, right. For the definition of the stress, we were dealing with a vector quantity. All of you know that vector has a magnitude and direction. That is a very at a very fundamental level, or I would say at earlier classes you would have defined vector to have something magnitude and direction. Okay. So, for example, we took that small surface around the point P, right, and then said that let this be the normal of the surface and let this be the force or the resulting stress vector. Okay. This is nothing but let me call this as delta F, which means it is the force, and remember that we said limit as delta S tends to 0, okay, we defined stress as delta F by delta S. Oh, this is nothing but the definition of dF by ds. Obvious, I need not even specify that. This is nothing but dF by ds. Is that clear? And this is what we called as a vector T, because this is a vector, we divided this by an area, and hence T is a vector. Is that clear? Now, we put one n there and a squiggle at the bottom. Is that clear? This is to indicate that this quantity is a vector. Okay. Now, this is to indicate that this T depends upon the plane that you choose. We saw that already yesterday. Okay. Now, your question is, what do you mean by T1 n, T2 n and T3 n? That is the question. What do you mean by T1 n, T2 n and T3 n? What are these things? Is that right? They are nothing but the quantities associated when I resolve this vector in the x1, x2 and x3 directions. This you would have in your earlier classes you would have written T is equal to T1n I plus T2n j and T3n k plus. In this course, we are not going to use I, j and k because of the indical notations that I am going to introduce shortly. Hence, instead of I, j and k, I call them as E1, E2 and E3. Okay, they are called as the basis vector, right. So, T is now defined as T1 E1 plus T2 E2 plus T3 E3. So, this is a vector. we went ahead and derived a matrix ultimately for sigma and called this as state of stress at a point. Remember that we call this as a state of stress at a point. In other words, we said that there are 9 quantities with it. We associated 2 indices. We associated 2 indices with the sigma I and j. One index, the I index indicated the plane, j direction. Is that clear? So, I and j are 2 indices, whereas here what is the how many index? Only one index, right. Now, this being 9 quantities obviously cannot be expressed in terms of 3 bases E1, E2 and E3. There have to be 9 bases to express this. Let us not worry about too much of theory in tensors right now, but remember that this has 9 and that has 3. So, this is called as a second order tensor. People deal with this in a matrix form. Okay? That is the easier way for an engineer to deal with a second order tensor. It is an easier way to deal with a second order tensor. But though mathematically there is a difference between viewing it as a matrix and viewing it as a tensor, but for all practical purposes when we do manipulations with it, okay, the concept of matrix is extremely useful to us. Hence, we look at it as a matrix. Is that clear? Now, why did we define this? We had a long discussion and ultimately we came up with a relationship between the sigma and t. You remember what was the relationship? We said that, say for example, Ti n is equal to sigma ji nj. Is that clear? So, we came up with a relationship of this kind. What does this relationship tell us? It tells us that if you give me a state of stress at a point P, which means that you give me all the sigmas, sigma 1 1, sigma 2 2 and so on, okay, and if you ask me a question, what is the stress vector at this point P at a plane n, then using this equation I will tell you, or I can calculate and tell you what are the T1s, T2 and T3, or what are the Ti's rather. I will be able to tell you Ti's. That is what I mean by this expression. Okay. Now, let us expand this. Is that question clear? Is that clarifies your doubt? Please also note there was one more question, that what is T and what is N? They are totally different quantities, okay, or what is delta F or what is N? See, sometimes when we talk and when we use it, we have a tendency to say force and then say corresponding stress, okay, stress vector and the force vector. I think when you use it, it will become very clear the difference between the two, and obviously this definition here will tell us what is the difference. Is that clear? Okay. So, please note that both of them are different. One is the normal, the other is the force that is acting. Okay. That is the force that is acting, or the effect of the other body onto this body where P sits. Is that clear? Okay. If I consider a corresponding point in the other half of the body, remember I had cut it into 2 pieces, corresponding point in the other half of the body, then the force will be acting in the opposite direction, okay, like bar we did. I do not want to repeat what we did, but like that bar where we cut one side there is a force like this, the other part will have a force in the opposite direction. Is that clear? Okay. So, what does this equation now mean? Okay. There are indices, as I told you, they are summation indices, or there are rules for summation. These indices in other words, these rules are not based on a lot of physics, it is based on certain rules to make things easier for us. Okay. Why do you sum up? You can't ask a question because it is a convention, It's rather a convention. Okay, like for example, you write a vector with a bold letter, like that. Okay, it's a convention. What is the convention? The convention says that any vector or a tensor or whatever quantity it is, okay, can be expressed, or even a scalar can be expressed in terms of a letter and an index associated with it, okay, by means of a letter and an index associated with it. For example, V is a vector. All of us know that it can be resolved into V1, V2 and V3, and we express this as Vi. Is that clear? Okay. Sigma, what we just now saw, sigma, and we associated with sigma two indices which we called as sigma ij. Okay. I can associate, say for example, what is called as elasticity tensor, say C, with the indexCijkl. Is that clear? So these indices are not repeated, I and j are different and so on. Okay, they are free indices. At one level, at a very simple level, this also indicates the order of the tensor. Number of free indices indicates the order of the tensor. I can write, say for example, P as sigma ii by 3. Now there is a difference between this and this. What is the difference? What is the difference between the two? It gets repeated. I now gets repeated. Here it does not get repeated. Okay. Here it gets repeated. The convention here is whenever an index gets repeated, it means that you have to sum up, okay, over the range of that index, which means that sigma ii is equal to, what is it, sigma 11 plus sigma 22 plus sigma 33. Okay. So sigma ii is equal to sigma 11 plus sigma 22 plus sigma 33. Okay. Of course, here we have divided it by 3, it does not matter, just sigma ii means that sigma 11 plus sigma 22 plus sigma 33. Is that clear? Okay. Now, whereas here in this case, when I say about sigma ij, there is no repetition, which means that I and j takes values ranging from 1 to 3. So I have 9 different quantities, that is what it means. This means that I have sigma ij means that I have 9 different quantities, whereas when I say sigma ii, it means that there is only one quantity. So what is this sigma ii then? Whether it is a scalar or a vector or a tensor or a second order tensor, or what is that? Yeah, that is true. That is scalar, because there is only one quantity. Okay, there is only one quantity, and hence this is a scalar. So this kind of index, which does not get repeated, stands out free. Okay, tells me the order of the tensor. So this is a 4th order tensor. This fellow is a 2nd order, and so on. Tensors are also classified by transformation of coordinates. I will not deal with it in this class, I will take it up in a later class. Okay, that tensors also are dealt with from transformation. Okay, we will go step by step to understand it. Okay, let us not lose the thread, we will come to that later, but right now let us only worry about how to study or how to understand the indical notation. I know that they are difficult notations. It is not that always we put these indices as a subscript or below here. Under certain conditions, we can also, or we will also put it as a superscript as Vi. But in this course, fortunately, we will not use indices, okay, as a superscript, but it has its own meaning and so on. Okay. Now, we will only use it as a subscript in this course. When I go to superscript, then I have to deal much more with tensors, which I am not going to do, but we will deal only with this kind of indices. So, summation index, as you right now you would have understood or got a grip of it, is that whenever there is a repetition, you have to sum up. Okay. Again, these mechanics people have a convention. They say that as long as you use Roman letters for subscripts, like I, J, K, A, B, C, D, whatever it is, okay, these Roman letters, then the range of the subscript is from 1 to 3. So, when I say sigma I, my range is from 1 to 3. You can also use for subscript what are called as Greek letters. So, say for example, I can use alpha, beta, gamma and so on. I can use for example sigma, alpha, alpha, okay, subscript. For the instead of I and j, I can use alpha, beta, gamma and so on. So, when I use alpha, beta, gamma, my range is restricted to 2, or in other words, my range is 1 to 2. What does it mean? It means that sigma alpha alpha means that it is sigma 1 1 plus sigma 2 2, that is all. Sigma 3 3 does not come into picture. Only when I want the range to be 3, then I use I, j and k. Is that clear? Any questions on it? Okay. Right? Fine. Now, let us go back and look at this expression. Okay. Having clarified all these things, let us now write down this expression. Look at the left hand side and look at the right hand side. What do you see in the left hand side? You see one I. On the right hand side, you see I stands out or free, and j is what is repeated. So, what do I do now? I sum up over j. So, in other words, this expression can be written as sigma 1 I n1 plus sigma 2 I n2 plus sigma 3 I n3. Okay. This is for one I, where or one expression. Say I is equal to 1, rather I should say when I is equal to 1, I get one equation. Okay. Then when I is equal to 2, I get another equation. When I is equal to 3, I get 3 equations. So, the 3 equations, with each of the equation having 3 quantities, are summed up into one simple expression. Is that clear? Okay. Now, please note that this j is a dummy index. Because of the statement which we made just now, okay, I can replace j by k, for example. I can replace this by k. Will my expression change? No, it does not matter. But of course, when I replace it by alpha beta, it will change because I will lose one term. Okay. So, this is a simple summation convention. In your earlier classes, what you would have done, you would have put one sigma before it, and you would have said that by putting a sigma and I varying from 1 to 3 and j varying from 1 to 3 or k varying from 1 to 3. This is what you would have done. Now, instead of doing that, what is that I have done? I said do not worry about the sigma, putting a sigma here, do not do that, but whenever you get a repeated index, you sum it up. Note that your left hand side and right hand side should balance as far as these indices are concerned. What do I mean by that? Let me write one more small expression which we will use later, okay, to understand what I am saying. Let us write Cij KL epsilon KL. Just take a second to understand what this means. Look at that. You have Ij KL KL. What is this first one? It is a tensor, correct, but what is the order? Fourth order. Okay. What is this? Second order tensor. So, fourth order tensor now operates on a second order tensor. So, what it means? It means that this is something like a function which operates. You would have probably seen and understood very well, say y is equal to some function of x. Okay. More sophisticated fashion, you would have called this function as a mapping. Function maps x to y. Okay, right. You would have written it in a different fashions as you grow and as you take higher and higher levels of mathematics. You will first initially you would have called this as a function, then you would have called it as a mapping and so on. Okay, so you can say that this is an operator. It operates on epsilon KL to give one more quantity. Okay. Please note that this quantity has to be what? Correct. It has to be a second order tensor so that my indices balance each other. So, in fact, this is the famous expression for the stress strain relationship. See sigma ij, that ij fellow is here, okay, then KL is here and epsilon KL. Is it clear? So, ij KL epsilon KL. So, KL gets repeated. Okay. So, I will have how many equations, by the way? Totally how many equations? 9 equations, correct. I and j 1 1, 1 2, 1 3, 2 1, 2 2 and so on. So, I can have 9 equations and each equation will have how many terms? 9 terms, correct, because KL will have values ranging from 1 to 3. So, I will have 9 terms. So, totally I have to write 81 terms. Is that clear? Is it clear? Okay, 81 terms. What is that I have done? I have summarized the whole thing in one simple single equation. Okay? Fine. So, in fact, as you go along, in many books, they will not even use this kind of indical notation. What they will do is to write this as sigma is equal to C epsilon. Okay? Some books put 2 colons or colon rather 2 dots before it and so on. Okay? That is why, see, this convention, how to write it may vary from one book to the other. So, you have to look for it. Actually, these are tensor operations. We will not go into the details of it, but it is important to understand what these indical notations mean. Any questions? Yeah, there can be one small doubt. Sir, what happens when this KL gets repeated 3 times? 2 times is fine. Why not 3 times? Can I have one more term and have again another KL? Okay? Now, in tensor analysis, usually it is a bad practice, again I am saying it is a bad practice to write thrice, okay. It should not get repeated thrice, okay. But many times or a few times, I should not say many times, sorry for that, but few times it may so happen that you may have to write it again, it may so happen, in which case the convention is that we will abandon summation. Summation is not implied, okay. As far as possible you should not write it repeating it 3 times, you should write it such that it only repeats twice. Is that clear? Okay. Now, having understood this, we will move to slightly more difficult conventions. These conventions come from 2 letters called delta, written as delta ij, okay, which is called as Kronecker delta, and a permutation symbol epsilon ijk, which is called as permutation symbol. Okay. These 2 symbols have some special meaning to it. These 2 symbols have some special meaning to it. Let us understand what these things mean. Okay. Now, when these symbols, okay, now the first question that may ask is, what is so great about these symbols, or why is that these symbols are used? Why do you want to introduce this? Okay. Now, these symbols are used for easy manipulation, as you will see in a minute, right. So, first let us take this symbol. It is again a convention. The convention states that when I is equal to j, how many quantities are there by the way for delta ij? 9 quantities, okay. So, again it is a matrix, delta 1 1, delta 1 2 and so on. When I and j are the same, which means that it is the diagonal of the matrix, delta 1 1, delta 2 2 and delta 3 3, then this Kronecker delta takes a value of 1, takes the value of 1 when I is equal to j. Does not mean I, please note it is not I. Delta I has a different meaning, that is summation. When I is equal to j, that means 1 1, 2 2 and 3 3, then delta ij takes a value equal to 1. When I is not equal to j, Kronecker delta takes a value of 0 when I not equal to j. Can you recognize what this really means? Can you put down for a second this in a matrix form and tell me? Correct, unit matrix. So, when I look at it, it is 1 0 0 0 1 0 0 0 1. Okay, in a matrix notation, this becomes a unit matrix. Clear? Okay. We will look at small operations with this in a minute. Okay. Now, before that let us understand what is epsilon ijk. Epsilon ijk is a permutation symbol, can take on values with I ranging j k ranging from 1 to 3 like. So, it is a 3rd order tensor. This is a 2nd order and that is a 3rd order tensor. Clear? Now, as the name indicates, it is a permutation symbol, and hence we can write first 1 2 3 in a particular order, say. Whenever I j k is such that they take a clockwise order, That means epsilon 1, 2, 3, 1, 2, 3, 3, 1, 2 or 2, 3, 1, we say that the corresponding value of epsilon is equal to 1. These are clockwise. This is for clockwise 1, 2 and 3. Clear? Okay. Now, whenever I have anti-clockwise, instead of 1, 2, 3, 2, 1, 3, 3, 2, 1 and so on, okay, this permutation symbol is deemed to have a value. It is just an assumed value. We say that this will have -1 for anti-clockwise. Is it clear? Otherwise, whenever I get this index to be repeated, for example, epsilon I j k becomes 1, 1, 2, that is a part of it, 1, 1, 2 or 1, 2, 2 or 1, 2, 1 and so on. Whenever this index gets repeated, it is supposed to have a value of 0. Is that clear? Okay. We will do two simple problems to understand where or how we use this. Okay. Before we go further, we will just try to understand. Is there any questions on indical notations? Any questions? Okay. Now, I will give you a problem in just 2 minutes, so that just think about it and we will discuss it in a minute. Okay. I hope these questions are clarified, or all these things are okay, whatever we have done so far. Okay. Yeah, I know there are 1 or 2 more doubts. I will clarify it towards the end of the class. Okay. We will just follow what we are doing now. There is some doubts of the what I had done in the previous classes. I will clarify it towards the end of this class. Okay. Now, the first question is, what is sigma ij delta ij? Sigma ij delta ij. What is this? Is sigma ii. Okay. Is it diagonal matrix? No, it is a scalar. Very good. So, it is sigma 1 1 plus sigma 2 2 plus sigma 3 3. So, what is that you do? Simple. When I look at I and j for a delta, immediately I know that when I is not equal to j, I know it is 0. So, the only terms which will now be available for me to sum up are terms where I and j are the same. So, I just go ahead and put for these indices I and j to be the same. So, in which case sigma ij delta ij will become sigma ii. Okay. So, sigma ii. I will give you a tougher problem and slightly wait for a minute. Let us say C is a vector, and that is formed by our famous cross product. I want to now write how many quantities are there? C1, C2 and C3 or Ci. Similarly A, similarly B. I want to write this in terms of C i's in terms of A's and B's. Let me not use Ai's and B's. Okay, let us say A's and B's, A1, A2, A3, B1, B2, B3. Okay. Now, can you do this by using epsilon? That is the question. Can you do that using epsilon? What you do is do this, write it down as you know in terms of C1, okay, C2, C3, C1 in terms of A1, A2, A3, B1, B2, B3, and see whether you can introduce now epsilon. Okay, if you have questions, do you want a time, do you want a minute, or you want me to tell the answer? Just try it out for a minute. Okay. Now let me give you a clue. Ci, just verify this. Ci can be written as epsilon I jk aj bk. Ci is equal to epsilon I jk aj bk. Now note the repeated indices j and k. So C1, what happens to C1? You write it down in terms of j and k. Just check up whether you will get the same result. Yes. Okay. So how do you get this value? First one is, note that Ci, I will keep this as 1. So C1, okay, sorry, epsilon 1. When I put 1 1, what will happen to this? 0. Okay. Then 1 1 2, again 0. 1 1 3, again 0. So the first fellow who will have a value here is 1 2 3, right? 1 2 3, which will have a value of 1. So please expand this and check up whether you get the value, the cross product that you know of. I am not going to do it because it is very simple. It's as an exercise, you please do that. And now you will understand that the use of epsilon ijk is also there to easily write down expressions like this. Okay? Such expressions can be very easily written down, and we will have more and more use of these quantities later in the course. Any questions? Okay. Having learnt now the indical notation to a certain extent, we will go to study, okay, what is called as equilibrium equations. We will study equilibrium equations. Now, all of you know equilibrium equation, but what I am going to do is to express it more rigorously. I am going to express this more rigorously. What is an equilibrium equation? For a body which does not deform, immediately you will say sigma f is equal to sigma f, what is that? 0. Okay. Now sigma m is also equal to 0. One of the questions that can come to your mind is, why is that I am always putting sigma delta f and then looking at it as a sigma? Because for an equilibrium, sigma f is equal to 0, sigma m is equal to 0. Moment also should be equal to 0. You remember that when I had cut this body by means of a plane, remember we did that, and I had a point P, okay, and I had put only f there, I had not put m there. Okay. In normal continuum mechanics and solid mechanics, we do not consider m, moment. Okay. When you want to consider moment also, it gives rise to what is called as coupled stresses, which we are not considering in this course. We are not considering that in this course. Okay. So let us not worry about, when I cut it, and it does not mean that the body is under equilibrium even when sigma m is not equal to 0. No, it does not mean that. When I cut it and look at the influence, okay, we assume that, okay, m is equal to 0 at that point, and we do not consider m at all. Okay. So, let us now first consider what happens to a body when sigma f equal to 0. Let us put the body. Okay, that's the body of interest to us, and the body has two types of forces that are acting. What are the two types of forces? Body forces. Let us say that is the volume inside, sitting inside dV, and that there is a body force that is acting, and let me call this body force as, say, F. Please note it is a vector, okay. And there is also a surface force that may act on the surface, okay, say ds, and that surface force we can call it as, say, T. Is that clear? What is that I have left out? N. Okay. Now, the first thing that I am going to do is to write down an equation which all of you know. Sum of these forces is equal to 0. How do I write that down? I will first integrate all T's surface forces. So, it is a surface integral designated by S, Tn ds. Please note that it comes directly from, okay, from my definition. Okay. Now, so Tn ds, or rather I should say that it is a vector. Stress. I should not call this as, always I have a tendency to mix force and stress. So, let us, I hope when you are following it up, okay, you follow this as a, or a traction. I should call this as a traction and a stress, okay, vector that is acting. So, this would be the total force. I am sorry for that. This is the total force. So, whenever I put T and say force, what I mean is actually the stress that is associated. That the context will tell you what I really mean. Okay. This plus, what is the other thing? Body forces, where I have to take a volume integral. Okay. Always the students have a tendency to get scared about, volume integral and surface integral and so on. Okay. But what I am going to deal in this course is only the concept. Okay. Do not worry that you are going to do a lot of integration and you have to study this lot more and so on. I am going to only look at it conceptually, right. Now, with respect to volume, how do I write this? F dV is equal to 0. That is the equilibrium equation. Is that clear? Okay. It is possible to write this down in an indical notation, though I would not like to do it quite often, but it is possible to write this down in an indical notation as well, just for clarity, because we are just starting on indical notation. In other words, please note that this equation is valid for, or I can resolve T and F in 3 directions, valid for all the 3 directions. So, as a common factor for 3 directions, I can write it as, in terms of I, as integral S T I will take values from 1 to 3, N ds plus volume integral F I dV is equal to 0. Is that clear? Okay. Or in other words, T1 and so on. What is TIN? Sigma Ji Nj. So, I can write this as sigma ji nj ds plus integral v fi dv is equal to 0. Is that clear? Okay. At this stage, I see that one is a surface integral and the other is a volume integral. Now, I want to convert surface integral into a volume integral. How do I do that? Divergence theorem. Okay? Let us not worry about the intricacies of divergence theorem or how it is derived and so on. We will just write down the result of the divergence theorem. Divergence theorem is used to convert, okay, divergence theorem is used to convert the surface integral into a volume integral. Okay? Yes, I know some of you might have forgotten divergence theorem, so I suggest that you just have a look at it and come back. We will continue this derivation from the place where we left in the next class. But before we close, I want to clarify one or two things and introduce one small notation in order to write down the divergence theorem. Obviously, it is possible that we differentiate some of these quantities. Okay? Sigma ji or ij can be differentiated with respect to, say, x1, partial differentiation with respect to x1. So, I can write this as a dou by, say, dou x1, okay, or x2 and x3. So, in other words, I may differentiate this, okay, with respect to I and so on, okay, and then sum it up. So, whenever there is a differentiation like this, okay, I write this down as dou sigma ij, sigma ij comma j or comma I or comma k, which means it is the order will increase now. Please note that depending upon what I write here, the order will increase or decrease. Okay? Now, this comma indicates that I have differentiated it with respect to xj, okay, and j gets repeated, right. We will use that for divergence theorem in the next class, and maybe we will start the class with one or two clarifications which our friends have sought on what I have done before. Okay, I did not want to do it because I did not want to stop the flow of the stresses that concept of stress that we are dealing with, and hence I just carried on with it. Okay, so we will come back and recapitulate what all we did in this class and the previous classes. We don't lose track of it and go over to further definitions. Okay, so if there are any questions, we will start with those questions in the next class.